Hello and most welcome to 891 of the Heidegger series. And I would today read an article from the scientific magazine Nautilus. And I would put another twist to it. I will make a deconstructed twist to it. The title of the article is Quantum Mechanics is Putting Human Identity on Trial. And it starts with this little story. Have you ever heard the story of Martin Guerre? He lived with his bride and newborn son in Artigas, a small village in the Pyrenees foothills of southern France. In 1548, at the age of 24, after being accused by his own parents of theft, Martin Guerre disappeared, leaving his family behind. 8 years later, his parents had passed away. Guerre returned home, reunited with his wife, son, and fellow villagers. Over the next 3 years, Guerre and his wife Bertrande had 2 more children. All was going swimmingly until a foreign soldier came through the town and claimed that the man who returned was not the real Martin Guerre, but an impostor named Arnauld Dutil. The accuser claimed to have fought along Guerre in the Spanish army and said that Guerre had lost a leg in battle. Bertrand ignored the accusations, certain that the man with whom she was living was and had always been her husband. But soon, Guerre's uncle and Bertrand's stepfather joined the foreign soldier and accused the man of forging Guerre's identity and took him to trial. If electrons were distinguishable, all would be chaos, is the next. It is a story that has persisted in our collective imagination, having been made into a movie, a musical, a historical novel, a TV series and a Simpson episode, because it strikes an ever raw nerve. There is a sense in which our notions of identity are insecure. How can we be sure who someone is, even someone close? How can we be sure who we are, or that we are? What can identity mean in a world that is constantly changing? The early vitalist philosophers had a ready answer. Each of us is distinguished by a divine soul. Our physical bodies mere puppets animated by our invisible selves. But science has eroded this answer and sought identity in the physical body itself, which is true. Very good, Nautilus. At a microscopic level, promises the reductionist dream, there must be something to distinguish each of us from another. A hard-nosed foundation for our identity, one made of molecules and atoms. The path, however, is far shakier than it seems. Cast your gaze on Guerre, standing there in the courtroom. Zoom in, look closer at his face, his skin, his pores. Borrow down to his most basic constituents. There, see the electron. It's a building block of Guerre himself. But what if it were to put the electron on trial instead of Guerre? Yes, we can all giggle at the oddity of trying an elementary particle to the full extent of the law. Yes, we can all expect some cringe-worthy puns. Let's get them out of the way now, shall we? The air in the room is electric. The defendant is charged with the serious crime of identity fraud. Good. Let's move on. The judge rapes his gavel to call the court order to order. 12 jurors sit at attention. The defendant squirms in its seat. To the chagrin of its attorney, and the frustration of the sketch artist. An electron, any electron, is an elementary particle, which is to say it has no known substructure. Air was made of molecules, molecules are made of atoms, atoms are elementary particles, but elementary particles are at the end of the line. They are made of nothing, being as they are, the most basic building blocks of the material world. An electron is a point, taking up quite literally no space at all. Every electron is defined solely in terms of its mass, tiny, its spin, a half. An electron needs to spin 2 times to get back to its original position. And its charge, which is negative. Those 3 features comprise in toto the complete and comprehensive identity of the electron, as its want for spatial extent bears no room to house any further attributes. What does this mean? That every electron is the precise spitting image of every other electron, lacking as it does even the slightest leeway for even the most minuscule deviation. Unlike a composite, macroscopic object like air, or anything else in our everyday experience, electrons are not merely similar, if uncannily so, but deeply, profoundly identical, interchangeable, fungible, mere placeholders, empty labels that read electron and nothing more. This has some rather curious and measurable consequences. See here how sameness and difference turn out to be the same thing at this level. Consider the following example. We have 2 elementary particles, A and B, and 2 boxes. We know each particle must be in one of the 2 boxes at any given time. Assuming that A and B are similar but distinct, the setup allows for 4 possibilities. A in box 1, B in box 2, A and B in both in box 1, A and B in both in box 2, or A is in box 2 and B is in box 1. The rules of probability tells us that there is a 1 in a 4 chance of finding the 2 particles in each of these configurations. But on the other hand, particles A and B are truly identical. We must make a rather strange adjustment in our thinking. For in that case, there is literally no difference between saying that A is in box 1 and B is in box 2, or B is in box 1 and A is in box 2. Those scenarios originally considered 2 distinct possibilities are in fact precisely the same. In total, now there are only 3 possible configurations, and probability assigns a 1 in 3 chance that we will discover the particles in any of them. Experiments confirm that the microworld obeys the 1 in 3 statistics. Swap out the accused with another of its kind, and the universe would register no difference, neither would we. Score 1 for the defense. To drive the point home, the defense attorney calls to stand one Frank Wilczek, a theoretical physicist from MIT, for expert testimony. To establish his status as an expert, counsel recites Wilczek's credentials into the record countless books and scientific papers published, a protected list of awards won. Oh, the attorney smiles, and a Nobel Prize. The prosecutor looks begrudgingly impressed. Dr. Wilczek, the defense attorney begins, you have stated that you believe to be the most profound result of quantum field theory. Can you repeat for the court what that is? The physicist leans in toward the microphone. That 2 electrons are indistinguishable, he says. The smoking gun for indistinguishability, and the direct result of the one in three statistics is interference. Interference betrays the secret life of the electron, explains Wilczek. On observation, we will invariably find the electron to be a corpuscular particle, but when we are not looking at it, the electron bears the properties of a wave. When two waves overlap, they interfere, adding and amplifying in the places where their phases align, peaks with peaks, troughs with troughs, and cancelling and obliterating where they find themselves out of sync, where a trough and a peak coincide. These interfering waves are not physical waves undulating through material medium, but mathematical waves called wave functions. Where physical waves carry energy in their amplitudes, wave functions carry probability. So although we never observe these waves directly, the result of the interference is easily seen in how it affects probability and the statistical outcome of experiment. All we need to do is to count. One can't help but to wonder whether it's the electrons who are so devious, or rather space itself. The crucial point is that only truly identical, indistinguishable things interfere. The moment we find a way to distinguish between them, be they particle, paths, or processes, the interference vanishes and the hidden wave suddenly appears in its particle guise. If two particles show interference, we can know with absolute certainty they are identical. Sure enough, experiment after experiment has proven it beyond a doubt. Electrons interfere. Identical they are, not for stupidity or poor eyesight, because they are deeply, profoundly, inherently, indistinguishably, every last one. This, gentlemen, is no minor technicality. It is the core difference between the bizarre world of the quantum and the ordinary world of our experience. The indistinguishability of the electron is what makes chemistry possible, says Wilczek. It is what allows for the reproducible behavior of matter. If electrons were distinguishable, varying continuously by minute differences, all would be chaos. It is the discrete, definite, and digital nature that renders them error-tolerant in an erroneous world. The identicalness means that while we can speak of electrons generally, we are barred from making any statements about any particular electron. If you have two electrons and later observe two electrons, but you didn't watch them at immediate stages, you cannot say which one was the original one. Says Wilczek, it's not just that you are confused, it's impossible in principle to tell which was which. Peter Pesek, a physicist, historian, and a musician at St. John's College in Santa Fe, New Mexico, puts it this way. We could make a statement like, there are 5 electrons. We can give them a cardinal number, but we could not give them an ordinal number. Cardinal numbers are counting numbers, 5 electrons. Ordinal numbers are ordering numbers, the first, the second, the third, the fourth, the fifth. To say that we can have cardinals without ordinals is to say that we can attach labels to the group, but not to any of its individual members, which is itself to say that its members are not individuals at all. That's very surprising, Pesek continued, because we think of cardinal and ordinal numbers as if they always both apply. At the microscopic level, that's not true. You have one without the other. The trial goes on, and the prosecutor slowly backs and forth in front of the witness's stand, considering his cross-examination. Perhaps, he suggests, we can distinguish electrons not by their inherent features, but their location in space. Even if two electrons are in every way identical, surely we can tell them apart by the mere fact that one is here and the other one is there, can we not? Wilczek's reply is a simple no. While corpuscular particles appear to occupy specific points in space, waves by their very nature do not, and that's important. Tried to explain that many times. The functional wave doesn't have a place in space. No place in space. Remember that. And so when particles like our electron go on watch, they become diffuse and placeless. Their wave functions, though concentrated in particular regions of space, stretch out to infinity, so that there is always a small but non-zero chance that their particular nature should manifest itself anywhere, should someone decide to go looking for it. When no one is looking, the electron isn't anywhere, but merely has the probability to be found in various locations. So a fact so strange that one can't help but wonder whether it is the electrons who are so devious, or rather space itself. What happens to space when we're not looking? Does it simply fall away? Wilczek puts it this way. Another aspect of quantum mechanics closely related to indistinguishability, and a competitor for its deepest aspect, is that if you want to describe the state of two electrons, it's not that you have a wave function for one and a separate wave function for the other, each living in three-dimensional space. You really have a six-dimensional wave function that has two positions in it where you can fill in two electrons. The six-dimensional wave function means that the probabilities to find in each electron at a particular location are not independent. That is, they are entangled. The identicalness of electrons not only cripples the concept of a thing, but also the concept of space. In the old way of looking at things, we had space and then we put things in it. In the quantum view, we have things like electrons, and space emerges as a way to describe the complex set of relations and interdependence among them, with localized points like here and there peeking through like the tips of icebergs. When two particles are entangled, their properties, their identities, reside in neither particle individual, but in the relationship between them, a relationship that flaunts the usual constraints of space, bypassing it with what Einstein called spooky action at a distance. We got in this problem that particles of matter are often entangled, so says philosopher James Ladyman of University of Bristol. The state of the world can't be written as the state of all the particles separately. They are all tied together. The identicalness of electrons, of all particles, not only cripples the concept of a thing, but also the concept of space, revealing them to be opposite sides of the same feeble coin. It is a clue that there is something wrong with the way we cut the world into parts, a clue to a kind of holism, an underlying oneness. One what? Question mark. Some, like Wilczek, say one field. It is no mystery that all electrons look alike, he says, because they are all manifestations, temporary excitations of one and the same underlying electron field, which permeates all space, all time. Others, like physicist John Archibald Wheeler, say one particle. He suggests that perhaps electrons are indistinguishable because there's only one. But it traces such convoluted paths through space and time that at any given moment it appears to be many. Gottfried Leibniz, the 17th century philosopher, put forth the principle of identity of indiscernibles, which said if you can't tell two things apart, they are not two things. On one hand, electrons appear to refute the principle. On the other, perhaps the multiplicity of particles or the multiplicity of the world is a kind of funhouse illusion. Time, it has been said, is what keeps everything from happening at once. In the same vein, space is what keeps everything from being one, or in Wheeler's word, what prevents everything from happening to me. But in the realm of the quantum, the scaffolding provided by space recedes, and with all the notions of identity and thingness, and with them the plurality of existence. The electron is everywhere, the electron is nowhere, a fugitive without a form, an outlaw sans alibi, and clearly innocent of identity fraud, by definition. But what about the human being that it builds? Zoom out. Bertrand Gare wife has always refused to believe that her husband was a fraud. But during his trial she changed her mind, deciding that although the man claiming to Martin Gare knew many intimate details of their early relationship, he was not the man she married. And yet, when the disputed girl turned to her and wagered that if she were to swear that he wasn't her betrothed, he would happily agree to his own execution, Bertrand remained silent. Martin Gare, now judged to be an Till, was convicted and sentenced to death by beheading. The doomed man appealed his case in Toulouse, insisting that he was in fact the true Martin Gare. He made such a compelling case that the judges of the appellate court were ready to acquit him when, to everyone's amazement, a man appeared in the courthouse claiming to be the real Martin Gare. He looked very much like the accused, except that he walked with a wooden leg. Although this Martin Gare was unable to recall many convincing details about his earlier marriage, Gare's family and townsfolk were immediately convinced this was Martin Gare. The man who stood trial was hauled off for beheading, while Bertrand begged her husband for forgiveness. In its decision, the court decided that Till was not Martin Gare. But what does that mean to be Martin Gare? Is it an act of persistence? It is to connect by some smooth and seamless trajectory to the Martin Gare of every moment in space and time, following what Einstein called the word line with a perfect fidelity and without deviation. Zoom in again. Gare consists of fundamental particles, but their word lines are not lines at all, just a series of points separated by strange and sundered lacunae. The electron's word line is, in the words of Wheeler, a great smoky dragon with a well-defined head, a distinct tail, and nothing but vapor in between. What we call reality, Wheeler said, consists of few iron posts of observation between which we fill in by an elaborate papier-mâché construction of imagination and theory. What this shows for reality and the idea of the ontic move is that as we start to ask the question what and not why, we always end up in trouble, because identity is not a what question, it's a why question. And therefore, without quantum mechanics, there can be no salvation for education, academia, faith or anything else. We will be dissolved, as this example showed. We will be beheaded like Martin Guerre. But once we understand the previous question that was never asked, the why question, then we are saved, and we will also save identity. Although identity won't be as important for us, because we will have understood the really, really important question of why, which actually subsists in everything. Because as you understand, this is the solving of the subject and the object division, which is not really a division at all. The division is an illusion, and that division makes for the what question. But if you can move it along, you understand the actual movement is the why, and it should fit the why question, so to speak. The movement should fit the why question. And then all of a sudden you have a real world, and you have identity, and you have sameness, but you also have difference. The why question is the before question. And to get there takes a lot of work and a lot of undoing of the faults already put in place. We need to some extent unlearn what we put in place. This problem that is presented as a problem in the article is actually a solution. And it doesn't ask you the why question, which is good, because that is our job. And we come in and show that the why question is the most important, and then everything is saved. You decide how to zoom in, zoom out yourself, or reality does it, which is an even better answer. I say thank you very much, and thank you for your patience on this very occupied day. Bye bye for now. Cheers.